Hello everybody and thank you for tuning in. In this video I'm going to present you the basics of logistic regression and give you an intuitive explanation of how the cross-entropy error can be used to fit the logistics function to given data. To start things off, think of the following example. You are developing a device that is supposed to give suggestions for a good sleep. To train the device, you have tracked the hours you have slept and whether you feel rested afterwards. You know when to come up with a model for the device to predict whether you feel rested after a given amount of sleep. From your studies you remember that in some binary classification problems, the class conditional probabilities can be expressed through a sigmoid function that has been fitted to the data. This prediction method is widely known as logistic regression. The open question is now, which parameters have to be chosen for the sigmoid to represent the data well? To do this, we first have to find a mean to quantify how well the sigmoid is fitting. This can easily be done by summing up the error between target and prediction for each data point. For negative samples, the error is the prediction value itself. For positive samples, it is 1 minus the prediction value. If we want to include the separate error terms in a single formula, we can modify it slightly to impose a selection based on the class label. This is already looking good, but we can do even better by penalizing large prediction errors more than smaller ones. As our error terms are in the range between 0 and 1, we can achieve that by taking the logarithm of them. The logarithmic error values are indicated by the dashed lines. Finally, reorganizing everything gives us the error formula to be used in logistic regression, which is called the cross-entropy error. Now that we can evaluate the function's fitness, we can simply find the optimal parameters by minimizing the error. Unfortunately, there exists no closed-form solution to this problem. Luckily, the problem can be solved iteratively instead, for example with gradient descent. Following along the path of the smallest gradient, we end up with the optimal parameters for a model being a gain of 3.7 and an offset of 7.17. And that's it. Thank you for watching.